Okay, this one is Giancoli Physics AP Edition, 7th edition. We're working in Chapter 10 Fluids. This is general problem number 75. Let's go ahead and jump into it. That problem reads, a beaker of water rests on an electronic balance that reads 975 grams. A 2.6 centimeter solid copper ball attached to a string is submerged in the water, but does not touch the bottom. What are the tension in the string and the new balance reading? So go ahead and wrap your brain around this problem, see if you come up with a plan. Let's come back and compare notes. Okay, let's see what you came up with and how it compares. As always, we're going to go through and identify some quantities we're working with. We have a 975 gram, that's for the beaker. So let's declare that mass. I got a copper ball, so B might be confused with ball. How about just that? We'll leave it at that. Leave it by itself. We have more masses, we'll use something else. I have a 2.6 centimeter diameter solid copper ball, so that's the diameter of the copper. And since they're giving me a diameter and it's saying it's solid, I'm going to assume that's a sphere. We're dealing with copper here for our material. We'll probably look at density for that later. It's attached to string, submerged in the water, does not touch the bottom or the tension. Okay, so they're asking for a tension in the string. Let's use F sub T for that one. And then they want the new balance reading. Now again, these balances are actually measuring force, but they read out in mass. So it converts it based on gravity. So they're really asking us for the mass reading or mass apparent. We have to be careful here because they're asking about the reading on the beaker. So I'm going to compare this mass apparent to the mass of the beaker here. We often use this mass apparent as the mass apparent of the thing being submerged. We have to be careful with that. May need to come up with another subscript later. Let's go and start with this. Now to help sort out a picture here, let's go and draw a beaker. The beaker's sitting on a balance here. Got water in it. Now what's happening is we're submerging this copper into the beaker. And normally when we do these sorts of problems, we're talking about the tension in the cable, the apparent mass of the object that's submerged, the densities here. The somewhat different question here is about the new balance reading. So conceptually what's happening is when we submerge the copper in the fluid, it will push water out of the way, it will displace water. That water will push back on the sphere, making the sphere's apparent mass go down. But to look at the beaker, the concept is if the water is pushing on the sphere to decrease its apparent mass, then the sphere, by Newton's third law, is pushing back on the water that's in the beaker that's pushing on the beaker. So whatever apparent mass or what mass reduction we have on the sphere here is going to be the same as a apparent mass increase on the beaker. Maybe we label that delta mass up here. So I'm going to add that delta mass, or take the decrease in the apparent mass on the copper will be the same as the increase in the apparent mass on the beaker. So we'll add the delta here to this mass to get that mass. That's how we'll approach this. Let's go ahead and start with our copper here that's being submerged. So we work on the tension. So for the copper, draw a free body diagram for our copper. We have the force of gravity pulling down. We have a buoyant force pulling up. It's going to be less than the force of gravity because it does submerge. And I have not used subscript B yet, so we can go ahead and use B for buoyancy. And I'm also going to have a force of tension in this string. It's the combination of this tension and buoyant force that's going to offset this gravity. So if we do a Newton's second law, this over here is going to be a zero. There's no system acceleration. So we're going to have all these forces over here. They're asking for tension, so we won't have a G in that. So we're going to have to be a little bit careful here. force of tension plus the buoyant force minus the force of gravity is going to equal 0. Therefore, the force of tension is going to equal the force of gravity minus the buoyant force. That should not be a huge shocker. And for buoyancy, you can use this equation down here to calculate the buoyant force. Now remember, this buoyant force is the result of the displaced mass of water, which is the density of water times the volume of the water, times the acceleration due to gravity. But this volume here, since we don't really have a way of calculating directly the water displaced, this volume here that's displaced of water is going to be the same as the volume of the sphere, since it pushes the water out of the way. We're going to use the volume of the sphere there. Sometimes we have to use a mass density comparison there, but in this case they do give us a geometry, so we can make that substitution fairly easily. Our tension is going to be the force of gravity, mg, common substitution, minus the buoyant force, which is going to be the density of the water we're displacing, times the volume of the water, which is the same as the volume of the sphere, which the volume of a sphere is 4/3 pi radius cubed. Again, they give us the diameter, so I'll have to cut that in half. That is also going to be multiplied by g. Gives the buoyant force. Now we know the mass of our object. No, we don't. We do have the volume and the shape, and we know the material, so we can get the mass. So we do have to use another density mass volume replacement here. Remember, density is mass per unit volume. So any mass we can replace with the density times the volume. So we need to make that substitution as well. Again, this is the mass of the copper ball that has gravity pulling on it. This is the force of gravity. So that mass can be the density of the copper times the volume of the copper, which is the same as all this hot mess over here. And there is an acceleration due to gravity there. Same volume here. And to save some wear and tear in our calculators, let's go ahead and factor out all the common terms, which is basically the volume and the acceleration due to gravity. So we get 4/3 pi radius cubed times g. Then it's just times the density of the copper minus the density of the water. That copper density we can look up in a table or on the internet. Same as the density of water if you don't have it memorized by now. But at this point, you have the force of tension in terms of a bunch of numbers I know. Now we're ready for those numbers. Got to watch for unit conversions as we go. The first unit conversion we're going to be concerned with is the radius of this sphere of copper. It's 2.6 centimeters. It's the only length dimension here. We got some cubic meters over here, so we're going to need this in meters. Let's go ahead and convert this to 0.026 meters, and then, oh, by the way, that's the diameter, so I have to cut it in half. So it's 0.013 meters. 0.013 meters for that radius. We're going to cube that times the acceleration due to gravity. We're going to take the difference of the densities. Now, for density, we're looking at copper, and then water. Copper is 8.9 times 10 to the third. And that's kilograms per cubic meter. And for water, it's simply 1 times 10 to the third, or 1,000. Also kilograms per cubic meter. Now, because we did our conversions, these cubic meters will cancel with those cubic meters, so that shouldn't be a problem. We're going to end up with kilogram meters per second squared. That is a mass times acceleration, which is a force. So that makes sense for our tension. Now this here is essentially 9,000 minus 1,000, about 8,000. That's going to be a really small number. This is going to be a small number. So let's go ahead and grab a calculator to see what we get. Okay, after punching that into their calculators, we approximately 0.71248-ish newtons. That is a very small quantity of force. In our problem, we're dealing with, we got 4 significant figures there, but we only have 2 significant figures there on the diameter. So we're going to go and round this to 2. And our force of tension in our cable on the copper is going to be approximately 0.71 newtons. Now that takes care of that part of the question. Then the other question they asked us was, what is the new balance reading? And again, the concept here is the ball displaces the water, pushes the water out of the way. The water pushes back on the ball, but the ball's pushing on the water. And so the water is going to push back. It's going to push on the jar. So the change in the mass, or the apparent change in the mass, is going to be transmitted or transferred to the jar. So the new mass on the scale, we give that a name, guess the apparent mass. The new mass on the scale is going to be the old mass. We're going to add to it the change in the mass due to the water that was displaced. Apparent change in mass due to the water displaced is the mass of the water that was displaced, which is the density of the water times the volume. And that volume is going to be 4/3 pi r cubed. So if we take our original mass of our beaker, 975 grams, and we add to it the apparent change in mass due to the density of the water displaced, that number should be getting familiar if you've been working with these problems for a while. Multiply by 4/3, multiply by pi. And the radius we used before is 0.013 meters. Cubed. Now we're going to pick up our calculators and see what number we get here. Now I went ahead and did this calculation. I did overlook one unit conversion issue here. This is 975 grams, not kilograms. This is going to spit out kilograms. My calculator gave me 0.009228-ish kilograms. I don't add that to the grams, so let's go ahead and multiply by another 1,000 here to make that grams, which make that 9.203 grams added to this 975. When you add that 9 and some change to that 975, you get 984.20 grams. And again, with the number of significant figures we have in this problem, it's 2. We're going to round that off to about 980 grams. That is the new reading on the scale due to the mass of the displaced water. So that should take care of it for this one. Moving on to the next.